Hello everyone, and welcome to the first lecture video for our Class 9 series of lecture videos. We'll continue with our discussion of radical reactions. Next, let's look at the radical bromination of propane. So here we start off with a propane molecule, diatomic bromine. We could use heat or light. If heat, probably around 200 degrees C. For a nice balanced reaction, we get 1/2 of some probable 1-bromopropane and half of 2-bromopropane and HBr. And as we explained earlier, light is symbolized as H nu and heat is symbolized as delta, and these types of quote-unquote reagents indicate a radical initiation. So what is our statistical expectation for the production of either 1-bromopropane or 2-bromopropane? Well, we need to look at the numbers and types of hydrogens on propane. So there are 6 primary hydrogen atoms on propane and 2 secondary hydrogen atoms for a total of 8 hydrogen atoms. So what is the percentage that are primary? Well, 75%. And what are the percentage of hydrogen atoms that are secondary? 25%. So if bromination is a statistical process, we would expect to get 75% of our 1-bromopropane, otherwise named as N-propyl bromide, and 25% of 2-bromopropane, or isopropyl bromide. You will need to be able to identify types of hydrogen atoms and calculate an expected statistical ratio. So, the observed ratio experimentally is very different from our statistical ratio. As we said, we expected from pure statistics 75% of 1-bromopropane and 25% of 2-bromopropane. Experimentally, wow, we get 92% of 2-bromopropane and only 8% of 1-bromopropane. So what's going on? Well, this brings up the idea of a relative reactivity ratio. So we know from our experimental observations that the secondary hydrogen is far more reactive than the primary hydrogen. So how do we define relative reactivity of a secondary hydrogen versus the relative reactivity of a primary hydrogen? In this case, it will be the experimentally observed amount of percentage of 2-bromopropane divided by the number of secondary hydrogens there are that could have led to that product. So there are 2, compared to the percentage of experimentally observed 1-bromopropane divided by the number of hydrogens that could have led to that product, which are 6 primary hydrogens. And so we get a ratio of about 35 to 1. So the reaction is very selective, and so we have to ask why. In this case, the RDS, that is the rate determining step, is the product determining step. So we will illustrate the difference. We have 2 possible reactions. After initiation, we produce bromine radicals. That bromine radical could bump into our propane and either abstract a primary hydrogen, leading to this primary propyl radical and HBr. And the difference, the change in enthalpy for that is plus 14 kcals per mole. Or our bromine radical could bump into the propane molecule and abstract a secondary hydrogen, one of 2. I've only drawn 1 there, but I know that you know, after we abstract that and leave a radical behind there, you still know that there is 1 other hydrogen attached to that carbon. And of course, we're producing HBr. What is the change in enthalpy for this elementary step? It's 11.5 kcals per mole. So there's a difference. This elementary step, this pathway, is higher in energy by a significant amount in terms of energies that differentiate pathways. So let's look at a energy versus reaction coordinate diagram. Like I said, we start off with propane. Here's our bromine radical. We're using Hammond's postulate. Our transition state occurs late because it's endothermic. The more endothermic, the later. Creating the primary propyl radical is a more endothermic process than creating the secondary propyl radical, hence our transition state is a little bit later in the reaction coordinate diagram. So this is an issue of kinetics versus thermodynamics. Like I said, we used Hammond's postulate to rationalize the observed selectivity. Transition state structure looks like the radical intermediate. The secondary radical must be more stable than the primary radical. We already know the reason why. That's hyperconjugation. We discussed this in a prior video looking at radical stability. So the factors that stabilize the transition state are the same factors that stabilize the secondary radical. Here, we can approximate the activation energy as roughly the change in enthalpy. For highly endothermic reactions, this is a fairly good approximation. So it turns out that a 1.4 kcal per mole difference in the activation energies for two possible pathways leads to a 10-to-1 selectivity. And there happens to be an exothermic, a logarithmic relation to this. So a difference in energy of 2 times 1.4 kcals per mole or 2.8 kcals per mole leads to a 100-to-1 selectivity. So 10 times our 10-to-1 selectivity. And so if this is a difficult idea to wrap your minds around, let's revisit our general chemistry for just a moment.